Suppose that we have a vector and we want to transform it into another vector alpha prime. This can be done by acting T, which is a linear transformation, on alpha. Any linear transformation in a complex vector space has some special vectors which are transformed into scalar multiplies of themselves. These vectors are called the eigenvectors of the transformation, and the complex number lambda is called the eigenvalue of the eigenvector. Note that the null vector is not an eigenvector. For a particular basis, this equation can be written in the matrix form. Putting all our matrices on one side of the equation gives this expression in which 0 is a matrix with 0 elements. Now, if t minus lambda I has an inverse, we can multiply both sides by t minus lambda I inverse, and A yields 0, which is not an eigenvector. But if the determinant of t minus lambda I is 0, the matrix is singular and doesn't have an inverse. So to find the eigenvalues, we need to solve this determinant. This equation yields a collection of lambdas. At least we have one distinct eigenvalue and at most n different eigenvalues. This is called the spectrum of the matrix. Note that if two or more linearly independent eigenvectors share the same eigenvalues, we say that the spectrum is degenerate. Let's find the eigenvalues and eigenfunctions of this matrix. The first step is to calculate this determinant and find its roots. Let's choose this column to calculate the determinant. We use the only non-zero elements multiplied by the matrix of cofactors. The determinant has three roots, as you can see, 0, 1, and I. The next step is to use lambda 1, lambda 2, and lambda 3 to find the eigenvectors. Starting by the first one, we get three equations, and we need to find a1, a2, and a3, which are the elements of the first eigenvector. Now let's find these elements. From the first equation, we find a1 equals a3, and the second one yields a2 equals 0, and the third equation has nothing new. Any multiple of an eigenvector is still an eigenvector, so we can say a1 is equal to 1, and so a3 equals 1. Now we have our first eigenvector associated with lambda 1. For the second eigenvalue, we have three new equations. We can do the same thing for these three equations, and let a1 equals 2 and find the second eigenvector. And finally, for the third eigenvalue, we have this eigenvector. We first find a1 to be 0, so a3 is 0 and a2 is undetermined. So we let it be 1. And here is the last eigenvector. So these are the eigenvectors and eigenvalues of this matrix. Like this example, if the n-dimensional matrix has n distinct eigenvalues, it can be represented as a diagonal matrix in its eigenspace, meaning that its eigenvectors span the space and the linear transformation T can be represented in this space as a diagonal square matrix with eigenvalues on the main diagonal.